Okay, well, sorry about the lag in the first video. I was just losing my concentration and it's pretty late. So, I have this Newman projection and I'm going to try to draw it. This is pretty hard with just one hand, but here we go. So, I have bromine here. CH3 down here, the hydrogen over here. I drew the CH3 here. The hydrogen down here and the hydrogen down here. Okay. So here's one of our Newman projections. Now the idea is that every conformation of the Newman projection, we are just simply taking this molecule back here, carbon number 3, and we're rotating it to 60 degrees. I think that's about 60 degrees. Yeah, okay. So here's the new one. Draw it really fast. Okay, let's see it from the model again. There we go. Okay, there. Okay, I hope you see that. We'll just draw the last one. It's, once again, you simply take the back carbon, the carbon number 3, and you rotate it another 60 degrees. There you have it, okay? I think you can draw this on your own. Okay, so the idea behind this, well, I'll draw it because I need to make a point, but just simply okay, so here are our 3 projections, right? Now, first of all, I'll talk about the energy just relative to each other. This, I've been trying to tell you, is the lowest energy conformation. That's because the bromine and the methyl are 180 degrees from each other. This bromine is it's a large molecule, right? And it has steric strain if it's close to these CH3 groups. in this molecule there is no steric strain between the CH3 right here, because the bromine is surrounded by only hydrogens. In this next one over here, there is steric strain between this bromine and this CH3 right here. This is a bond angle of 60 degrees. You can say there is a gauge interaction between the CH3 and the bromine. It's the second lowest energy conformation. Now for this one in the middle, there is not only CH3 and bromine steric interactions, a gauge interaction between this bromine and the carbon in this CH3, but they also have a gauge interaction between the CH3 and the CH3. There is two gauge interactions right here. It's the least stable and the highest energy conformation. Now, this conformation right here, it is not going to react in an E2 reaction. The idea is that only the bromine and the hydrogen that the base is going to pull a beta hydrogen that is anti-periplanar. We use the term anti-periplanar because it's not exactly 180 degrees, it's close to it. So they say it's anti-periplanar, but for now we'll just call it antiplanar. Now it has to be opposite of the bromine, which is in this, the middle one, and this one on the left. This hydrogen and the bromine are anti-periplanar to each other, or antiplanar. Now I'm going to take this first one right here, and I'm going to see, let's just see it in, first of all, Newman projection, so I make sure I got this correctly. I have the CH3 down here. There was a gauge interaction on the top, so I'll just rotate this really quickly. Okay, right here, this is the molecule right here in the Newman projection. Do you see that there's a hydrogen and anti-periplanar? I'm trying to touch it with my pinky right here. That's their anti-periplanar hydrogen. This is going to be the one pulled off in an E2 reaction. If we go over here to this guy, the one in the middle, I just need to rotate the bond. Boom. There we go. This is, once again, touching it with my pinky. That's your hydrogen that's going to be reacting in the E2 reaction. I'm going to try to make it into a ball and stick model as well and show you how the antiplanar molecules look in just the regular line drawing. There we go. Swear. Okay, so it looks like bromine towards us. Okay, now crap. I totally forgot. Which one? Oh, okay. This right here. It's behind me. I'm trying to hit it with my pinky. See, this goes all the way back, away from me, this hydrogen here, and the bromine goes towards me. This would be the anti-periplanar bromine, the anti-periplanar hydrogen to this bromine. They would be pulled in an E2 reaction. Draw that really quick. Something like that. Even though I didn't draw that molecule correctly, the bonds. Because I have this guy going down, this carbon going down instead. But yeah, that's the idea. Sorry, I'm trying to get the molecule correctly in the correct orientation as my drawing. I think that's it. Not perfect, but I hope this helps you out. I'm still not quite understanding how your program works. I'm still trying to figure out what the hell it means by dihedral angle, your 4 atoms in the dihedral angle, but I guess what I can tell you, if we take this, I'll just redraw my Newman projection here. Bromine, hydrogen, hydrogen, hydrogen. Now the 4 atoms in a dihedral angle between this bromine and this CH3 would be the CH3 back here. There would be a CH3 back here. It's connected to the CH3, you don't see it. And then in this molecule right here, we have a CH. I believe it's CH2. No, it's just CH1. Yeah, it's this carbon, whatever the hell it is, and then this bromine. These 4 atoms, CH3, CH2, CH, and bromine, are all participating in this dihedral angle of 60 degrees. If we were talking about the dihedral angle between this and this would be 180 degrees, and the atoms would be the CH3 here, the carbon back behind, and then this carbon here, CH3 down here, and the CH down here. The atoms between this interaction would all be carbons. So that's what I've been able to figure out. Well, I hope this helps you, okay? See you later.